Okay, so now I'm going to be doing the fall 2021 exam 3. This exam, however, even though longitudinal stability is on exam 2 this year, there are a lot of longitudinal stability questions on this exam. So, problem 1. Consider an aircraft which has a vertical tail mounted at the nose of the aircraft ahead of the center of gravity. Considering only the influence of this vertical tail, the presence of a non-zero side slip beta, is this aircraft stable? In the presence of a non-zero side slip beta, is this aircraft stable in yaw such that the side slip beta is reduced? So, up until now, we haven't been taught this, but basically no. The aircraft is not stable in yaw such that the side slip beta is reduced, since the resulting yaw moment produced does not restore the aircraft to symmetric flight. With a vertical tail mounted at the front of the aircraft, a positive beta creates a side force from the tail that causes a negative yawing moment, which does not reduce side slip. So, if you're curious about that, that's the answer, but for exam 2, that doesn't have to do with longitudinal stability. So, okay. I think it has to do with lateral stability, but okay. Problem 2. A conventional fixed-wing aircraft is flying at trim, straight level, unaccelerated flight, and has the following lift and pitching moment parameters. Assume that in trim, lift equals weight, and the dynamic pressure is equal to that, and gravity is 9.81 meters per second. Part A, write out the lift and pitching moment equations for trim as functions of the angle of attack and elevator deflection using the values given above. Let's look to our equation sheet. And we have this useful equation right here, which relates CL trim to alpha and the elevator deflection. We are going to multiply that out for CL trim and CM naught. And that's the equations with respect to alpha and elevator deflection. Part B asks determine the elevator angle required to trim the aircraft. So now we've got 2 equations and 2 unknowns. So we're going to solve both equations for one unknown and then set them equal to each other. You could, however, solve this by solving for one variable, which you don't know, alpha or elevator deflection, and then plugging that into the other equation. But here I solved for alpha, and then I set them equal to each other. And then this step is a little bit too far ahead, so you don't need that right now. And then you continue to simplify that to try to get the one unknown on one side, which is the deflection of the elevator. And then we've got this, and then you plug in all your knowns, you know everything here, and you get the elevator deflection in radians. Problem 3. An engineering team investigating the dynamics of an aircraft flying in trim determines that the eigenvalues of the longitudinal modes are as follows. The aircraft has a mass of 5,800 kilograms. Assume that in trim the lift equals weight and the aircraft and the thrust equals drag. The gravitational constant G is 9.81 meters per second. So this is actually a really important question, and they're probably going to ask this on exam 2 for longitudinal stability. It's analyzing the eigenvectors of the longitudinal matrix, which is this whole matrix right here. And so these are the eigenvectors of this matrix when all those parameters are plugged in. And so part A says state which eigenvalue, so those were the eigenvalues associated with this matrix when all of the values are plugged in. Okay, so part A says state which eigenvalue belongs to the short period mode and which belongs to fugoid mode. So we know that fugoid mode has a really small natural frequency and really small damping ratio, and it's the opposite for short period. So we can just look at these components right here and see that they're bigger, and then look at this equation right here. We know that the real part plus the imaginary part, both squared, and then taking the square root, is the natural frequency. So clearly the natural frequency of this eigenvalue is going to be greater than this one because these have smaller components of the real and imaginary parts of the eigenvalue. So we know that this has a much larger natural frequency. So the eigenvalue of vector 1 and 2 must belong to the short period mode, and that the other one thus must be the fugoid mode. Part B, find the natural frequency and the damping ratio of the fugoid mode. Okay, so this is the fugoid mode. We just determined that. So we can do all of this plug and chug of finding that the real part right here equals negative zeta Wn, and that the imaginary part right here equals this. So that's what I did right here. Or we can just skip all of the algebra and skip all this room for error by literally just doing Wn equals the real part, the square root of the real part, so 0.075 squared, plus the square of the imaginary part, and that gives us 0.1373, which is exactly what I got before by doing the system of equations. So literally just do this on the exam to save yourself all this work. And then what you can do is plug that in here to solve for zeta. That works completely fine. So part C is the natural frequency. What is the natural frequency of the oscillation of the fugoid mode? So that is WD. WD is literally the imaginary component. So you really could just skip plugging these numbers into this equation and just look what's the imaginary part of the eigenvalue. It's this. So that's the damping, that's the frequency of oscillation of this mode. Okay, so for part D, we want to find the use the fugoid mode approximation to approximate the thrust needed for the aircraft to be in this trim condition and the speed of the aircraft in this trim condition. So on the left here, you can see in the notes, this is not on the equation sheet, but I recommend remembering these equations because they're super helpful. This one specifically, the damping ratio equals this. So that's what I'm using here. And then I know that since drag equals thrust and lift equals weight, because they told me that, I can replace this with thrust and this with weight. And since this is non-dimensional and this too is non-dimensional because it's newtons over newtons, that works fine, that substitution. And then rearranging, because we know zeta, we can find thrust using the zeta that we found above. And we find that thrust is this. And then using this equation right here, where ZU equals this, we know that CL equals lift over this stuff, but we know that lift equals weight, so we can just plug in mg. So now we know that it equals this. And then we want to rearrange so that we get U naught. And then we can plug everything in because we found this from the previous step right here. We find that the speed equals this.